Hello, everyone. So now we are just waiting for Professor Pedro, I think. Testing the audio. Can you hear me properly?
Sure. Nice.
Yes.
Yes.
Good morning and good afternoon.
Yes. So maybe that we are waiting for 2 or 3 minutes, and if Professor Fardim is not yet in time, maybe that Layde can begin its presentation, her defense, and I hope that Professor Fardim will be arrived as soon as possible. Okay?
Perfect.
Simone, are you hearing me?
Yes.
Simone?
Yes, I'm here.
I think it's better. You can do the welcome now before starting the defense. Just some words of welcome.
Ok. Essa frase não é igual? Essa frase? Acho que eu não sei. Eu coloquei, pode ver você. Mas o Pedro não entrou ainda. Just a minute.
Layde?
Maybe that we have lost Layde.
Yeah.
Sorry, everyone. We had a little problem with the connection here. Good morning, Brazilian members and public, and good afternoon, and French members. We start the
Oh,
I do like it.
I'm sorry. I'm sorry. I don't know if you hear the ring, but there is a fire alert. There is a fire alert in my building. So I have to leave during, I'm sorry, 5 or 10 minutes, no more.
Okay.
So I cannot stay here.
Okay.
I believe that it's just an alert, and I will come in 10 minutes, no more. I'm very sorry, it's not my fault. See you in a few minutes.
Okay.
Good luck.
Wow. Simone? Não. Simone?
Oi?
Fala
me
alguma
ouvindo?
coisa, o som tá muito ruim de você. Fala.
Ruim o som? Será que
É.
eu...
Fala.
Peraí,
Tava
vai ajustar
cortado.
aqui.
Ah, eu acho que é a internet,
Ah,
professora.
melhorou. Melhorou.
Melhorou? Ok. Melhorou.
Cabo de rede?
Muito bom.
Não, cabo de rede.
Uhum.
O computador não conecta.
Não. Seria melhor. Aí ele voltou.
So just for people that is watching on YouTube, I'm leaving this message for letting know that we have some delay in the starting of the thesis defense, and as soon as possible, we are going to start.
Hello, everyone.
Hello, Jean. It's all right.
I'm so sorry. I hope it's all right now. Otherwise, 800 people outside of the building. Okay, now it's perfect. I'm sorry.
Okay, that's good. So starting again, I'd like to thank all jury members from Brazil and from France, and for the evaluation of the thesis of Layde. And in the meeting room, we can also find Gabriel and Pedro for the technical support. Okay? Now, Layde, we start to present the thesis.
Yes, Professor Jean.
Okay.
Yeah.
Jean,
Yes. Yes.
I pass the word for you. Okay?
Yes, just a few words. So now it's time to begin. So, well, my name, I have to present myself. My name is Jean Coudane. I am emeritus professor at the University of Montpellier, and I work in research at the Institute of Biomolecules Max Mousseron in the Polymers for Health and Biomaterials team. So I am rather a specialist in everything concerning the chemistry of polymers for health and preferably biodegradable polymers. So now maybe it's time to begin. I would like to remind you the main points of this jury. In order, we'll give the floor to Layde for around 45 minutes, and after her presentation, we'll ask her some questions. The first question will go to the two rapporteurs and then to the other members of the jury. And I will finish with a few questions before giving the floor to the thesis director and co-director. So now it's time to Layde to present her work. So Layde, as you like.
So let me just share here my presentation. Maybe you all can confirm if it's possible to see. Just a minute. Here. Can you all see the presentation?
Yes.
Yes.
Yes. For me, it's okay.
Okay, great. So first of all, I would like to thank the jury member for accepting the invitation of this thesis defense, evaluating this thesis defense. And I would like to also thank everyone that is here watching this thesis defense. Today I'm going to present my thesis subject, which corresponds to the development of pullulan-based drug delivery systems for the cancer treatment. So many strategies is normally applied for the cancer treatment, and basically they correspond to surgery, radiotherapy, and chemotherapy. They can be applied in a single way or even the combined way, for example, chemotherapy and radiotherapy and surgery and others. So nowadays, different strategies can be applied for developing a better cancer treatment, which correspond to target therapy, immunotherapy, gene therapy, and also the development of drug delivery systems by the encapsulation and the development of different drug forms for the oral or other ways of administration. So polymers are normally an alternative way for preparing the drug delivery systems, since it corresponds to a versatile material which can be flexible with chemical modification. You can have different properties for polymer when you apply different chemical modifications, for example. Besides, some polymers can be biocompatible, which means it can be administered in the body and without causing any side effects or toxic effects. And some polymers can be also biodegradable, which means after the administration in the body, it will be totally degraded and eliminated by the body without leaving inside us remaining materials. Pullulan is a polymer, natural polymer, it's a polysaccharide based in a composition of glucose units connected by alpha-1,4 and alpha-1,6 linkage, which is produced by the fungus Aerobasidium pullulans. So among the many advantages that pullulan has, it is biocompatible as expected, it's biodegradable, non-toxic, it is neutral, and it's hydrophilic, which means it presents a solubility in water. So pullulan is suitable for chemical modification since along the backbone of the polysaccharide, we have many hydroxyl groups which can be easily modified. Pullulan, however, is underused when it comes to oral administration, which corresponds to a new strategy and an interesting strategy for the development of drug delivery system. Therefore, pullulan is a promising material for biomedical application, especially for the development of drug delivery systems. Erlotinib, it's a chemotherapeutic agent already applied in the market, which is a target therapy corresponding to a small molecule of tyrosine kinase inhibitor of epidermal growth factor receptor. It's normally used for the treatment of non-small cell lung cancer, but also for pancreatic cancer in advanced stage, which means with metastasis stage. However, erlotinib is pH dependent, which means its solubility will depend on the pH of the medium that erlotinib is dissolved. For example, at a pH 2, erlotinib has a solubility of 0.5 milligrams per milliliters, and it changed to 0.007 milligrams per milliliter when the pH comes from 2 to 6.8. For example, when oral administered in the stomach, it changed the solubility after goes to the duoden and the intestinal absorption. Therefore, erlotinib is classified as class 2 in the BCS classification, biopharmaceutical classification system, and it corresponds to a molecule with high permeability but low solubility. Therefore, different strategies can be applied for improving the solubility of this drug. For example, the development of amorphous solid dispersion or co-crystal or particle size reduction or the encapsulation by a polymeric matrix, for example. Therefore, some questions we need to make to see what we are going to develop. The first one is what material we are going to use. The second one, which process should we apply for we obtain this drug delivery system? And finally, which drug delivery system we may develop? So, solid dispersion is an alternative for the development of drug delivery system. It corresponds to the dispersion of the drug inside a polymeric matrix, and it can be classified in 3 types: amorphous solid solution, in which the drug is dissolved in a amorphous polymeric matrix, and this solubilization it presents a low amount of the drug. We can also have amorphous solid dispersion with high concentrations of the drug dispersed in an amorphous matrix. And we can have the crystalline solid dispersion, which presents the drug in a crystalline form mixed with the polymeric matrix, which is amorphous. So the objective of this thesis was the preparation of particulated solids or solid dispersions based on pullulan as a new career for improving the erlotinib solubility and oral administrated. Among the objectives, we have the first objective, which was the synthesis of new polysaccharides based on pullulan. We have then the preparation of microparticles using spray drying, microparticles using hot melt extrusion, and nanoparticles using nanoprecipitation by dialysis method. So, focus on the first objective. We have then the chemical modification of pullulan, and it has already been published in a reactive and functional polymer. To prepare the chemical modified pullulan was first reacted with DEAE, which corresponds to a cationic molecule, and it was prepared in a neutral medium containing sodium hydroxide and DEAE. After the preparation of pullulan-DAE, it was copolymerized with PZLL using 3 different amounts of the monomer polylysine. It was in 3 different amounts of monomer, obtaining then 3 different polysaccharides. So, with the polymer, it was used the chemical characterization, physical-chemical characterization, and biological characterization to analyze the polymer characteristic and choose the best condition, the best polymers for further application. And in the chemical characterization, it's possible to observe that the synthesis of pullulan-DAE was successful performance with the peaks correspond to A and D, in which the D peak and the carbon NMR, the D peak has a displacement after the chemical reaction. And with the hydrogen NMR, it was possible to observe the chemical modification, but also it was possible to use the hydrogen NMR to calculate the degree of substitution. So it means that every 100 glucose units along the pullulan backbone, we have 15 molecules of DEAE. So the degree of substitution was 0.15. For the copolymerization, the carbon NMR demonstrated that the copolymerization was successfully performed since there was the disappearance of the peak I. It corresponds to the elimination of CO2 occurred during the chemical reaction. And with the hydrogen NMR, it was also possible to determine the different degree of substitution for each copolymerization. So what is noticed is that the increase in the amount of the monomer resulted also in an increase in the degree of substitution in our copolymer. The molecular weights obtained, it is observed that there is no significant difference between pullulan and pullulan-DAE. However, for the copolymers, what is noticed is the presence of peaks correspond to a higher elution time, which demonstrated that when higher amounts of the monomer was applied, we had a homopolymerization of the PZLL instead of a copolymerization. So the thermal analysis of the 5 polymers observed that in this condition, the performance condition, all the materials show thermal degradation, temperature proper for spray drying or hot melt extrusion, making them possible for further application. Analyzing the characteristic of each of the polymers, it was performed the fluorescence technique to see the critical aggregation concentration of the copolymers to analyze the amphiphilic characteristic. And what was observed is that with higher proportion of the monomer, the critical aggregation concentration reduced, which was expected since we included along the pullulan's backbone a higher amount of hydrophobic content. So for the cationic property, it is noticed that the presence of DEAE in fact resulted in a cationic property, which was evaluated by zeta potential, and therefore the synthesized polymer presented the 2 main properties that we made, which is the amphiphilic property for the copolymers and the cationic for all the chemical modified polymers. So the biological analysis was also performed, and what is noticed is that the mucoadhesivity test that showed that even pullulan or chemical modified pullulan with DEAE presented the mucoadhesivity capacity, and it was influenced by the concentration, which means when higher concentrations of the polymer was applied, the mucoadhesivity present in the mixture increased. The cytotoxicity test of this polymer was performed, and what we can notice is that even under 72 hours of incubation and higher polymer concentration, no cytotoxicity was presented. So the polymers present a possible alternative and for biomedical application, especially for the development of drug delivery systems. Therefore, as a conclusion of this first step, we have that the pullulan was successful, chemical modified, and the materials presented the characteristic that we aim for further application. And pullulan-DAE with 25%, the copolymer with 25%, was chosen as the best material for further application in the next steps, since the other polymers show the presence of homopolymer along the mixture. Therefore, as next step, we have then the title of this thesis, which is the development of pullulan-based drug delivery for cancer treatment. To do so, each polymer was applied for different technique. So, for hot melt extrusion, for example, the 3 polymers were possible to apply, since there was no need of solvent in this case. For spray drying, pullulan and pullulan-DAE was applied, and for nanoprecipitation, only the copolymer was applied, since it was the only material capable for self-aggregation. Therefore, the next step corresponds to the preparation of microparticles based on a spray drying technique. To do so, it's necessary to understand before what is the spray drying process, which is involved. It basically involves the atomization of a liquid solution into a drying chamber, and the atomization forms the drop, which will be in contact with the hot air and will dry in a powder solution, in a powder material that can be collected in the cyclone. So many parameters influence this process, such as the nozzle type, the atomization rate, the pressure, the relative humidity inside the dry chamber, the temperature inside the dry chamber, like inlet, outlet temperature, but also the feed flow rate, which means the rate that the feedstock solution will be pumped inside the chamber, and the conditions of the solutions, for example, solid content, viscosity, and also surface tension. So to first choose the best condition for pullulan and pullulan-DAE being spray drying, these 3 parameters were analyzed, and it was possible to see that with higher polymer concentration, pullulan presented a different behavior than pullulan modified. Pullulan presented a non-Newtonian behavior, while pullulan modified presented a Newtonian behavior under high concentrations. And when this viscosity was plotted in terms of the concentration, it was possible to determine that the concentration attainment for pullulan was much lower than pullulan-DAE, which means the chemical modification impacted the viscosity of the polymer solutions. So the surface tension was analyzed, and what was observed that pullulan presented a higher surface tension compared to pullulan-DAE, and pullulan-DAE presented a sensibility to the concentration. So when higher concentration was applied, lower surface tension was obtained. Therefore, for the spray drying technique, different parameters were evaluated, including the polymer concentration, which the maximum use was 6%, and the inlet and outlet temperature was settled between 120 and 150 for inlet, and 63 and 82 for outlet temperature. The nozzle type was also compared, including two-fluid nozzle, and ultrasonic nozzle. The 2 of them were compared. And all these process parameters were evaluated to obtain the best condition for further preparation of the erlotinib microparticles. Therefore, for the preparation of erlotinib microparticles, 2 different concentrations was applied, with different mass proportions. And it's important to emphasize that for pullulan, since pullulan and erlotinib present different solubilization, it was not possible to prepare a solution between them. So erlotinib in the crystal form was dispersed in a water solution containing pullulan for after posterior spray drying process. Meanwhile, for pullulan-DAE, it was possible to prepare a mix between erlotinib soluble in ethanol and pullulan soluble in water. So the mix was possible to prepare, obtaining a homogeneous solution proper for spray drying. Therefore, only pullulan-DAE was possible to apply in ultrasonic nozzle, since pullulan without the chemical modification was presented a dispersion and not a solution. As a result, we have that the two-fluid nozzle presented higher yield in the process compared to ultrasonic nozzle, and the polymer concentration also influenced in this yield. Higher concentration of polymer resulted in a reduction in the yield. As a particle size, it's possible to observe that the polymer influenced the average particle size, And what we have is that ultrasonic nozzle resulted in a more homogeneous particle size. And it's possible to observe when analyzing the same images that we have a more homogeneous particle size for ultrasonic nozzle. For pullulan, prepared with erlotinib, it's possible to observe that the polymer concentration also influenced in the yield, with a reduction in the yield when higher polymer concentration was applied. And in the particle size, no significant difference was observed, and as similar results as seen in the same images. For the thermal analysis, it was noticed that in both cases, a crystalline peak was observed since there is a melting peak presenting. For pullulan, it was already expected since we had a crystalline form of erlotinib dispersing water. However, for pullulan DAE, it was not expected since we had the mixture between water and ethanol with erlotinib and pullulan DAE soluble. Therefore, the melting peak present is probably due to the recrystallization process of erlotinib during the mixture between a solvent and a non-solvent. So, what we can conclude is that in both cases we have a crystalline solid dispersion. As the dissolution test of this erlotinib dispersed in a amorphous polymer, what can be observed is that in both cases, we have a controlled release. However, for pullulan, the controlled release were much more intense, since we have 25% of release after 120 minutes. And when we change the pH from 1.2 to 6.8, no inhibition of the recrystallization was observed. So the same behavior as previous erlotinib in the base form, in the pharmaceutical form, was obtained. So, as a main conclusion of these partial results, we have that pullulan DAE presented a real advantage compared to pullulan, since the chemical modification could make possible to prepare a more homogeneous solution, a mixture between them. And with pullulan DAE, the yields presented an improvement when chemical modified pullulan was applied. But for both polymers, a controlled release was observed when oral administration technique for mimicking the oral administration system, and a controlled release was observed, but without an inhibition of the recrystallization. As next step is the microparticle preparation by hot melt extrusion. So to do so, we must understand a little bit about the hot melt extrusion. Hot melt extrusion basically consists in a mixture between the polymer and the API, which is the drug system. This mixture is put inside a barrel with a high temperature, and the solid mixture will be further mixture inside the barrel with the help of the screw rotation, and along the barrel, it will perform the mixturing and melting both materials, resulting in a homogeneous mixture with the capacity to form amorphous solid solution, solid dispersions, or solid solutions. After this mixturing, both in a melt conditions, we have the living material under the die, which will be solidified after the contact with the temperature of the home temperature. So many parameters may influence, which is basically the material. The material must present a thermal condition, proper thermal condition with high degradation temperature, for example. The process parameter also influences, which is the feed rate, but also the screw type, which can be, for example, single screw or multiple screw, and the speed that this screw is going to rotate, as well as the barrel design and temperature may influence in the process parameters. So as preliminary evaluation, it was first observed that pullulan and its derivative was not possible to extrude alone. So it was necessary to blend with another polymer to make pullulan possible to extrude. And to evaluate which material is interesting for blending with pullulan, Hansen solubility parameter was calculated, and Hildebrand the pullulan and its derivatives were compared to Clucel groups, which is a group of polymers, HMP-CAS group, Eudragit group, as well as PEG, Etocel, Maltodextran, Soluplus, but the polymer which presented the closest solubility to pullulan was Clucel. So Clucel was chosen as the material to be blended with pullulan for extrusion, and it has other interesting property, which means it's non-ionic, therefore it won't interfere in chemical modification of pullulan. It's soluble in polar and water, polar solvents and water, and it's easily to extrude. And besides, it's suitable for drugs with low solubility under different pHs. With choosing Clucel, other tests was performed to evaluate the influence of Clucel in this solid dispersion. So what is noticed is that the presence of Clucel increased the soluble fraction of erlotinib. So it was further analyzed the recrystallization process, solubilizing erlotinib, finally adjusting the pH to see if it will change, the presence of Clucel will change the soluble fraction of erlotinib. And what was noticed is that Clucel, in fact, could increase the soluble fraction of erlotinib, but the combination of Clucel and pullulan could increase a little bit more, which is interesting for further application in the dissolution test. Therefore, to prepare the extrusions, it was first evaluated the best conditions, including different polymer ratio, temperature, screw speed, and recycling time inside the conical rotation screw. And it was chosen that 30% of pullulan and its derivative was the maximum amount of polymers applied, due to the fact that it was not possible to extrude higher amounts than that for pullulan, for the copolymer PDPL. So, for the preparation now of the amorphous solid dispersions based on erlotinib and pullulan derivatives, two different concentrations of the drug was applied. 20% and 30% of erlotinib was applied, and the conditions operated for all of them was 160 degrees Celsius for the temperature of the barrel, 150 RPM, and 3 minutes of recycling time. After the extrusion process was processing for all of them, after the extrusion, for the preparation of the microparticles, the extruded were cryo-milled, and after the cryo-milled, the microparticles was obtained. So, the microparticles characterization, the solid state of the microparticles, was noticed that there was a significant reduction. No presence of the crystalline peak was observed after the analysis in XRD technique, which showed that the solution, the solid dispersion that we have now, is in fact an amorphous solid dispersion. And for the microparticle, we had that the copolymers microparticle presented higher values than the other microparticles prepared, and the dispersity between the particles, pullulan and Clucel, presented the lower dispersity. Evaluating now the dissolution test of these materials, what we noticed is that the control release was also observed for the hot melt extrusion process. However, with the pH change from 1.2 to 6.8, the formulations prepared with 30% of erlotinib presented a delay in the recrystallization, correspond to 5 minutes, which is, even though it seems small, it can be a possible increase in the solubility of the drug. Therefore, it is observed that for pullulan, the mixture between pullulan and Clucel could in fact increase the soluble fraction of erlotinib. After 120 minutes, the concentration was still higher than the traditional erlotinib. For the copolymer compared to Clucel, in both cases, it was noticed also a control release in the kinetic parameters. And for the copolymer, the 30%, the formulations contain 30% of erlotinib also present an inhibition in the concentration. However, when analyzing Clucel, what is noticed is that Clucel could improve the soluble fraction of erlotinib, but there was no delay in the recrystallization when only Clucel was applied in the mixture. As main results that we have in this section was that pullulan was not possible to extrude, so it was necessary to blend with another polymer, and it was with the blend with another polymer, the amorphous solid dispersion was now successful, obtained by hot melt extrusion, and the Clucel could improve erlotinib solubility. However, the combination between Clucel and pullulan was more efficient. For the last preparation, solid dispersion preparation, it was applied the nanoprecipitation to prepare nanoparticles. To do so, only the copolymer was applied. So, the nanoprecipitation principle is based on polymer and drug soluble in a common solvent, which is dropped inside a non-solvent. With the drop inside the non-solvent, it reaches the maximum concentration possible to be soluble, and then after that, it started to agglomerate and get in the precipitation form. And the agglomeration can coagulate and form particle size with higher size. Therefore, different techniques can be applied for this, for the non-precipitation. For example, solvent drop. However, when we work with polymers that is only soluble in solvent with high boiling points, for example, DMSO or DMF, it's not possible to apply the evaporation solvent. In this case, nanoprecipitation via dialysis method is an alternative to replace the other techniques. And this technique corresponds to solubilizing the polymer in the drug inside the dialysis bag and put it to solvent displacement against water or a buffer solution. And what happens is the nanoprecipitation inside the dialysis bag. As a previous evaluation, it was analyzed at different concentrations and under different pH. And what was observed is that for lower concentration, the pH did not change the particle size. However, when high polymer concentration was used inside the dialysis bag, the pH influenced in the particle size. The pH showed an influence in the particle size with lower particle size under acid pH. When preparing the formulations now containing erlotinib was put in the mixture in the dialysis bag, and it was precipitated, and after drying using the lyophilization process. Many parameters was evaluated in this case, and what was noticed that as previously evaluated, under neutral pH, the particle size was much higher with a higher also polydispersity. So it was not possible to use the nanoprecipitation with the buffer in neutral medium. Therefore, acid solutions showed a better performance. However, what was observed is that under lower concentration of the polymer and in acid medium, a massive hydrolysis was observed, obtaining no material in the final dialysis process. In this way, it's possible to demonstrate that only formulations containing high polymer concentration was further applied in this case. What was observed is that between the formulations AF1 and AF3 resulted in a better encapsulation. Extra test was performed to see if we could neutralize this hydrolysis process. So the buffer was used, the acid buffer was used only for 2 hours, changed to neutral buffer after that. But even though it improved the particle size, it did not result in an encapsulation of erlotinib. So formulation in F1 and the F3 showed the better options for now. Analyzing the solid material, what was observed is that formulations prepared in neutral medium present the crystallinity parameters, which was expected since there was a massive recrystallization in neutral medium. And for formulations AF1, 3, and 5, AF1, we've had the higher amount of encapsulated erlotinib, also presents some crystalline peaks, which show that erlotinib can be present there in an encapsulated form, but also in a free form as crystalline. Evaluating the encapsulation efficiency, it was performed on washing in the nanoparticles to see if we can remove the free erlotinib from the solid dispersion. And what was observed is that for formulation AF1, a massive change was obtained, which means that erlotinib was in fact removed. The partial of the crystal form of erlotinib was removed. For formulation AF3, there was also a change in the drug encapsulation after washing it. For particle size, it was noticed a significant difference before and washing the nanoparticles in the particle size for the formulation AF1. However, formulation 3, there was no significant change. In the thermal analysis, no significant behavior was observed since there was a massive degradation after the thermal analysis. Therefore, it was not possible to be conclusive with the thermal analysis. Only a displacement in TG was observed. And evaluating the recrystallization, so to better understand which erlotinib is that is put in the mixture with the nanoparticles, it was evaluated the recrystallization process of erlotinib, and what is possible to see a different change in the thermal analysis, which means that erlotinib recrystallized presented a different melting point, showing that it's not similar to the crystalline form of erlotinib in the basic form, but it's also not similar to the salt form, since in the literature, the melting temperature found is different. For the crystalline analysis, for the same analysis, it's possible to see the difference in the morphology of erlotinib before the recrystallization process and after the recrystallization process. So, in this case, the erlotinib recrystallizer was also performed a dissolution test to see the impact. What was noticed is that erlotinib recrystallized present a controlled release, and after the pH change, it also presented a 5 minutes of delay in the recrystallization. So, just changing the crystalline form already changed the dissolution profile of erlotinib. And comparing erlotinib recrystallizer with the nanoparticle, what was possible to observe is that the nanoparticle could release more amount of the erlotinib, and unwashing formulation AF1 presented a more oscillated parameter, which may correspond to the delivery of free erlotinib, but also encapsulated one. At this nanoparticle, the very interesting result was obtained, since the erlotinib presents 15 minutes of delay in the recrystallinity, which shows an interesting result for possibly improving the dissolution profile of erlotinib. Therefore, as a partial result in this part, we have that pullulan-based grafted with polyrazine show the potential for drug encapsulation and forming the nanoparticles. The pH, however, has a strong influence in these nanoparticles, and the erlotinib recrystallizer in the formulation could impact in the dissolution test, and it differs from the salt form and the base form of erlotinib. So AF1 also showed a delay in the recrystallization in 5 minutes, which may be an interesting result. As final conclusion of this thesis, what we have is that for synthesis of material, we have a synthesis of a new material which was not synthesized before, and these new materials present the properties that we wish. The impact in this chemical modification was evaluated for pullulan-based with the spray drying process, so it was much easier to process pullulan chemical modified. And for the copolymer, the impact in the chemical modification was evaluated in the nanoprecipitation, obtaining the nanoparticles. And among the techniques applied, the 3 techniques applied to prepare these 3 forms of the drug delivery systems, it was possible to observe that hot melt extrusion actually demonstrated to be a versatile technique. Since it was not needed to use a solvent, it was possible to use the 3 polymers. However, pullulan presented the limit of extrusion limited, which was necessary then to blend with Flucel. In the drug delivery system, all the shaping forms demonstrated a controlled release. However, only formulations amorphous solid dispersions containing 30% of erlotinib could show the delay, the recrystallization, and also the nanoparticles prepared, the AF1 formulations based on nanoparticles. As future perspectives we have for this thesis is the chemical modification. So we can apply chemical modification of pullulan in different ways. We can increase the DS, the degree of substitution of DAE, for example. We can reduce the molecular weight. We can apply other techniques. For shaping the techniques, other polymers can be blended with pullulan, for example, and see and evaluate the impact of this blend in the dissolution of erlotinib. Or for the nanoprecipitation, what we can do is, for example, change the drug and see the capacity to the copolymer to encapsulate other drugs with a different pH. And in the drug delivery system, the biological analysis must be performed, evaluating in vitro or in vivo tests to see effectively the change in the solubility in other tests, in the biological test. And as well as the drug delivery system can be redesigned for remaining a long time in the stomach and be absorbed in the stomach instead of needing change from acid medium to neutral medium. As an activities performed along this thesis, 10 articles was published with one related to the thesis, 3 book chapters, 10 congress presentations with 3 oral presentations, a prize we will have win in the SFGP, which is a French Congress, and 3 teaching training was also performed. So I would like to thank everyone involved, my advisors who gave me all the support that I need, who received me in France also, Professor Inês, but the undergraduate researchers that has been with me, William and Ana Julia, the research assistant that I have from Giza and Antoine, who was a great helpful, and every group that was involved, including here in the USP and in the IMT Minerbi, but also FAPESP for the financial support that I received. And finally, I would like to thank everyone that was involved in a way with this thesis, my friends, my family, and everyone that is here watching our YouTube. And I would like to thank also the jury for accepting the invitation. So thank you.
Thank you very much, Layde, for this very interesting. Everybody can hear me? It's okay? Yeah. Well, this very, I would say, interesting, clear, I would say also didactic and dynamic presentation. So now I would like to hand over to the rapporteurs and examiners who will ask you a few questions. As there are many people, yes, as there are many people likely to ask questions, it will be, in my opinion, desirable that questions are not too long and not 1 hour for each people. Maybe that 20 minutes for each reviewer or examiner should be very suitable duration. Okay? So, now, I would like to hand over first, for the first rapporteur, Pedro Fardim, because I know that now we can have Pedro Fardim with us. Good afternoon, Pedro.
Yes, good afternoon.
And yeah, now you have around 20 minutes to ask Layde some questions.
Okay. Thank you very much. And my apologies, because I just landed in Brussels and there was a problem with the airplane. I could not, my apologies for being late and for causing a delay in Brazil to you all. My apologies. So great. I really enjoy reading your thesis slide. It's a very nice piece of work. You start with the pullulan, and then you do the chemical modifications of this pullulan, and then you do a concept that not many people do. That's about the shaping and combining the shaping with the applications of the shaping for specifically for drug delivery and with the focus in cancer applications. I really enjoyed it. Also, the fact that you are working with these solid dispersions and amorphous solid dispersions is also very interesting, very interesting topic. But I have questions, of course. Professors always have questions, so I'm here to challenge you a little bit today. That is your day. So the first question I have is on your chapter 2. At the beginning of the chapter 2, you talk about polymers as drug carriers. And I was surprised that you didn't say anything about synthetic polymers because there is a huge amount of work and literature on synthetic polymers. So I would like to know why you didn't mention it. And then I would like you to mention some of them. If you can mention a couple of them, just to know that you are aware of the literature.
Yes, sure. So at this point, in this thesis, I didn't need to work with synthetic polymers. I worked with chemical modified polymers and the copolymerization with the polylysine via na synthetic way. However, previous I have worked with synthetic polymers such as PCl, and I worked as well with other synthetic polymers like let me see, like PNVCl as well. So synthetic polymers is actually an alternative as well as natural polymers, and we can find in the literature many synthetic polymers which can be biocompatible, biodegradable, and present interesting properties for biomedical application. In this case, in this thesis, we chosen to work with polypeptide and a polysaccharide. However, as in a previous work, when I worked with PCl, it showed great potential as well. So I don't know if I could discuss more about the synthetic polymers that I have in my knowledge. And I have others like PMMA, which I have been in contact as well.
Yeah, but I just miss it on the literature because maybe on a thesis for the reader is good to give a little bit of information about the synthetic polymers also, because the way it is written, it goes directly. It seems that natural polymers is the only solution, but it is sometimes not, right? And then there comes another question: why pullulan? Why pullulan?
In fact, pullulan started in the research group. Professor Simone is here with me and she can clarify more. But pullulan started in this research group since we have here in the university another professor which works with the preparation of pullulan by the fermentation process using the aerobasidium pullulans. So when he gave us the opportunity to work with his material, we saw the potential of pullulan, and since 7 years ago, we have been working with pullulan, chemical modification of pullulan, and application as well.
Okay, then I would like to move to the chapter 3, and I have some questions about there when you do the modification of pullulan. The first question I have is in the materials and methods. You will start with the pullulan. You describe a pullulan starting with 120,000 grams per mole as molecular weight. But then, when you do the modifications, when you do the characterizations by GPC later, you have a much lower value for that pullulan, that is about 90 and so on. And this value changes when you do the chemical modification. I would like you to comment on that, why you have this value on the materials and methods, 120, and then later you have 90, and then after modifications, there are changes on the molecular weight.
So in this case, when we received pullulan, the people that gave pullulan for us gave also the table characterization. So they gave us some information about pullulan and the molecular weight average. So this was used in material methods, but yes, maybe we should change to the real one that we found in the analysis from compared to people that gave these materials to us. And the changes in the molecular weight, it is possible to see that when this analysis was performed, the standard used, the polymer standard used was PMMA. So was not the best condition to perform the GPC analysis. It was not the proper standard. Now what I know is that they actually have now the pullulan as a standard for the GPC analysis. Yeah. Yes, but before, when I performed this test, the other polymer was used as a reference, as a standard.
Yeah, I see. And then it goes to these molecular weights. When you have on a page 107, you have the molecular weight, and then when you do some deconvolution of these chromatograms there. And when I was looking at these results, I was wondering, do you think there are some heterogeneities on your polymers? I mean, of course, you have a molecular weight distribution, and when you do a modification, and even with lower DS, how this can you elaborate a bit about how heterogeneous your material can be, even if it is coming from a pure polymer like pullulan?
Yes, so pullulan, since it's obtained by the fermentation process, it's really hard to have a pullulan with a polydispersity close to 1. So sometimes the macromolecular change really vary. And what we observed is that a slight reduction in the dispersity when chemical modification was performed, probably due to the medium that was applied, since it was applied a very strong neutral medium, which can perform a hydrolysis, a slight hydrolysis in the pullulan backbone. And with the copolymerization, it is noticed that only in the copolymerization with 25% of polylysine, it was possible to observe a peak with a higher molecular weight. So this is the convolution process. In the convolution process, it was noticed that for pullulan containing 40% and 50% of the PZLL, the monomer, it was possible to obtain homopolymers. So many chains in different sizes was prepared in this condition. Only the one with 25%, it was present the peaks with the elution time similar to pullulan, or with a elution time lower than pullulan, which show a possible copolymerization.
But how many times you did this? I mean, you have a variation here. Did you repeat it? Did you make a synthesis and then you analyze one batch and then the second batch, a third batch, and you see if there is a variation between the batches, or you just made one batch, characterize it, and that's it?
Yeah, we did again the batch after I did one. In this case, we characterized it with one. But after that, we performed the others and we analyzed it, and it is varying. This value is varying as when we analyze it, but it remains similar for pullulan DAE with 25%. It remains similar, but when higher amounts of monomer was applied, we could not improve the copolymerization process. But in this case, in this analysis showed in the thesis, 1-in-1 was performed. And it's important to emphasize also that we didn't have the proper condition to analyze this GPC, because pullulan is not soluble in water when copolymerized. So we may solubilize it in the MSO, and the elution condition was water. We tested before to see if pullulan precipitate in this condition, and it didn't precipitate. So we applied this technique. Therefore, it may be influenced by the hydrodynamic volume as well, since it's soluble in the MSO and added in the GPC using the water solution, buffer solution.
And what was the rationale to add this functional group to pullulan? Why are you adding the DAA and not other functional group like just an amino group or trimethylmodium or other systems? Why you chose specifically this?
DAE?
Yes.
Okay. I chose this one because there's previous working demonstrating that the molecule presented a cationic property. So this is why it was chosen. There was some previous working demonstrating that pullulan DAE with higher concentrate degree of substitution could present, for example, the interesting career for gene delivery and showing an interesting cationic property. Besides, the molecule was easier to modify with pullulan. The reaction was simple because sometimes when we go to a reaction, the complex reaction with pullulan, what happens is that we cannot recover a lot of material.
But then there is a question, why did you get a DS of 0.15 in comparison with results of literature of 0.65? So what's the reason for your lower DS?
I used lower amounts of DAE because I didn't want to change many groups of hydroxyl along pullulan backbone, since it was necessary to have some hydroxyl groups available for the further copolymerization. I didn't want to change totally the hydroxyl groups along pullulan backbone.
Okay, and your aim was to add, why cationization? Why did you choose cationization? You want the delivery to be at the stomach. That's the goal.
Yeah, before, when we were working with, we wanted to have like, we didn't expect it to work with oral administration when the polymer was synthesized. So the main goal before was another one, was encapsulating to deliver like parenteral way by parenteral way for cancer cells which have the different pH. So this is why we chose the cationic before. And then when we have the possibility to work with erlotinib, so it changed it to oral. And what we have is some impact in the cationic property, which influences also in the encapsulation of erlotinib.
Yes, because for delivery in the stomach, maybe amino groups are also quite interesting, yeah? Because yes, we have experience with amino groups and they were quite nice in this pH 1 to 2. It's very nice for the delivery. Then I have a question about your AFM. You make some results on AFMs, and you talk about stiffness and adhesion. But I was a little bit lost here because to talk about the stiffness and adhesion, you need to do some shaping here, right? What did you do? You make a film. You made a film of this pullulan. You make a particle and so on. It was not clear on the experimental part. And for me here, what does it mean? Because there are some changes, interesting changes.
Yes.
But what is that? Can be from the shaping, can be from functionalization. What is that?
From the chemical modified surface, maybe also. This technique, the mucoadhesivity technique, as well as the AFM, it was performed to see if the polymers could be applied in a drug administration in a mucosa. For example, the extrusion could be applied as well as auto-dispersible film for the oral administration. So it was a previous evaluation of the parameters that we have in the polymer to see what was the ways that we could go with this material. So we saw that pullulan presents a mucoadhesivity. It's positive. It has a mucoadhesivity. The stiffness, the adhesion, when analyzing with the AFM, showed difference when chemical modified pullulan was applied. But we chosen to work with microparticles because it wasn't available the machine to prepare the films. So we worked with the microparticles in this case.
So you use AFM on the microparticles?
Yes, we can also use the microparticles in mucoadhesivity way, like in absorption of mucus. So it's also an alternative, but for that, further study may be performed.
Okay. Then if we go to the chapter 4, I'm looking at my time here. Yes,
it's perfect.
It's perfect, yes. I'm looking at my time. On the chapter 4, on figure 40, you talk about, you have some entanglement concentrations of aqueous solutions for the pullulan and for the derivative of the pullulan, for the first derivative. And then you have a preparation of these particles with this system, and the particles you obtain, or the powder characteristics you obtain, the powder has much of the derivative. The particle size is much smaller than the particle size only of the pullulan, right? I would like you to discuss this and maybe link this with the process of chemical modification.
Okay, so what we have is that when this microparticles was prepared, the concentration applied for both polymer was 3%. This concentration is close to the concentration entanglement of pullulan. However, it's far from the concentration entanglement for pullulan DAE. It's lower. Here, it may occur that it could increase also the particle size was that pullulan presented the higher in concentration entanglement, and an agglomeration was observed, especially if we see the sand images, an agglomeration of the particle occurred. In the spray drying process, it was possible to see the forming of filaments, and these filaments can agglomerate the particle and result in a higher particle size. But the analysis of particle size, it's important to also emphasize that it was both performed in a non-solvent, and it's dispersed in a non-solvent, but therefore it's more compressible to observe the sand images, since it can be, for example, pullulan DAE can absorb it a little bit more, or can be precipitated a little bit more using this non-solvent when dispersed, and it can slightly change the particle size. It was difficult to find a common solvent for analyzing all the particle size in this case, especially when we have erlotinib in the mixture. And I'm not quite sure if I could understand, but I compare the concentration entanglement to the particle size. What I can observe is that since pullulan presented the concentration spray dried for pullulan was close to the concentration entanglement, it was not possible to have separated particle size, and what is possible to observe is more aggregated particle size with the presence of filaments in the mixture.
Yeah, I see in your sand pictures. And maybe I have my last question here because I see the time. So my final question to you is, when you are making particles, where is the API? Is the API, for example, when you are doing the nanoparticles, is the API inside the particle? Is the API on the surface of the particle? Is the API everywhere? Where is it?
Yes, it's a trick questions. We didn't perform it for the analysis, like microscope analysis, like then to evaluate, in fact, how it's encapsulated. But when in the theory, what we expected is that it's encapsulated in an agglomeration of polymer, because we have in the polymer part, which is hydrophilic and can interact with water, and also we have the hydrophobic, but also cationic, which may interact with erlotinib in the medium. So in my head, what I have from the theory is that it's encapsulated, but not in a micelle, for example, or a vesicle. It's more encapsulated in agglomerated particle size.
Okay. Thank you. I have a lot of more questions, but I don't want to make my colleagues unhappy because they also read the thesis and they have a lot of questions. So thank you very much and congratulations for your work. Thank you.
Thank you very much, Professor Fardim, and congratulations for the respected time. Now, I would like to give the talk to Abdelhamid Elaissari, who is your second rapporteur.
Thank you so much. Thank you, Mr. President, for giving me the role to talk now after my colleague who asked a lot of questions. First of all, I would like to thank your supervisors for giving me opportunity to be in this jury member. Okay, principally from Simone, which I know quite well a few years ago. Okay, first of all, the manuscript is really very good manuscript. You have a lot of results, a lot of things to discuss, in fact, okay? I don't know if you already published all this result or they are in progress to be published. They are in progress.
Sorry?
Did you publish all the results that you have in the manuscript or not yet?
Yes. Actually, in the manuscript, especially for the nanoparticles preparation, we performed many other tests here in the laboratory. I think it was the most challenging thing was the nanoparticle preparation. And here we evaluated many strategies, and we have other results that it's not here in the manuscript, but also what we are planning is to do the further analysis to better understand, for example, erlotinib recrystallized, for better understand the dissolution performance in vitro test, and if it's necessary in vivo as well. So it's just, I think there's still much other ways to go from this manuscript.
Okay, good. Okay, I really found your manuscript very interesting and easy to read. Okay, and we'll manage. Regarding the talk, I found the talk a little bit fast. Okay, I don't know if you are afraid about the alarm from Montpellier or not, but it seems that a little bit fast for me. Okay, then it's hard to catch some explanation from your talk. Okay, in order to well understood or better understand what you have done in your manuscript. I have only a few questions. You did, how do you control the colloidal stability of your particles when you are using spray dry system?
How do you control the
colloidal stability? Because you spray your particles, right? Then after that, you disperse them in water in aqueous phase. But how do you control the colloidal stability?
The stability after dispersing?
Yeah.
No.
Because when you dry the particles, after that?
Actually, the microparticles spray dried. I'm not applying for like a dispersion. So the dispersion was the solid preparated was applied in a. It was dispersed in water.
Only on solid part.
In the solid part. It was dispersed in water when analyzing the erlotinib dissolution test. It is in this moment.
Yeah, this is why. In any case, if you have any formulation and at any time you are using these particles in aqueous phase, they might agglomerate. They might have clusters. Okay? Then the relays that you are investigating, it's not good to my point of view. Because the dispersion is not homogeneously dispersed.
Yes.
Okay, but anyway, how do you control the particle size using such process? Spray dry system, how do you control the particle size?
The particle size using the spray drying? We could see that the nozzle was really influenced by the particle size, so we can perform these controlling. The particle size also was slightly influenced by the temperature. So the temperature is a drying temperature was inlet and outlet temperature was a way to control this particle size. As well as the concentration also could be applied, the viscosity applied in the solution. So I believe that.
Okay, but let's say if you need to have small particles, what will be the key parameters?
I would change the atomic nozzle to the atomic nozzle with a small overture, because I worked with 0.7 millimeters of atomization. But for example, here in the laboratory, we have the nano atomization, which is the nano spray drying, and we can reduce by changing the spray drying system, for example, the size of the atomization nozzle.
And if you reduce the concentration of the polymer, it may reduce the particle size?
If I reduce the concentration, I will change the viscosity, but not in this case, it wasn't observed a reduction in the particle size when the concentration reduced. So what I would change is the atomization nozzle. I would change the atomization nozzle, for example, from a normal, let me say, like a spray drying with 0.7 milliliters of opening space.
A
nano spray drying, for example, so that I can change. And as well as another strategy that I was thinking to improving this particle size was doing the reduction in the molecular weight of pullulan.
You think that if we reduce the molecular weight, we reduce the particle size?
I think we could, with reducing the molecular weight, I can get a less viscous solution, and I can apply, for example, in the nano spray drying, obtain nanoparticles. Because in the nano spray drying here, it's not possible to apply this pullulan, since we can have some problems in the equipment.
Okay, because we are working on spray dry and we have a big problem also to control the particle size. And this is why we are trying to investigate different kind of parameters. But until now, it's not easy.
Yes, I would reduce the molecular weight of the polymer and see if we can optimize this. Because this was some problem that we have here in the laboratory, because we work with nano spray. So what we did to reduce the particle size was actually change the nozzle. For example, it was a good option. And but to operate with this nozzle, we must have a less viscous solution.
Okay. It seems to me that in your manuscript you discuss the zeta potential of the polymer. All right. I think that you describe this in page 93 or something like that. Okay. Are you talking about the zeta potential of the polymer itself, or the zeta potential of microparticles formed by the polymer?
The zeta potential. The zeta potential was performed in a nanoparticles preparation. It was prepared first the nanoparticles, and with the nanoprecipitation technique, and after the nanoprecipitation of the polymer without the drug, it was performed the zeta potential.
And was it positive or negative value?
Was positive.
Okay.
Positive value. And we did also a titration. So the same solution was performed in a titration, changing the pH. Okay. And in this case, it was necessary to prepare a copolymer without the DAE to see the impact of the DAE in the molecule. So we did the synthesis with pullulan and the copolymerization without the first chemical modification. And then we compared this polymer without the DAE with the polymer with the DAE. So what was noticed is that these two nanoparticles presented a significant difference in the zeta potential. With the nanoparticles containing DAE, it was observed that under low pH, it presented a positive zeta potential, and it was reducing along the titration.
Yeah, I see. This is very positive and coming to basic pH.
Yes,
And
until
for
it gets
other one,
close to 10.
a non-modified one is almost non-charged, all right?
Yes, without the DAE, it was
With the
copolymerized
yeah, all right,
because
all right.
without the copolymerization, we couldn't analyze it.
Yeah, all right. I'm a little bit surprised why you are using atomic force microscopy. What you are looking for using atomic force microscopy?
We are looking for better understand the capacity, the adhesion capacity of the microparticle surface. As I previously said for Professor Fardim, before we wanted to perform like by hot melt extrusion, auto-dispersible film, which needs in my polymer, I need the adhesion capacity and mucoadhesive capacity. So this was why we performed to better understand as well as the chemical modification, how the chemical modification impacts in this adhesion.
Okay. Because to my point of view, using atomic force microscopy, it's a little bit hard to see exactly the morphology because it's contact mode, right?
Yes, and what we saw in the literature before is that to have a better result in these analyses in the atomization force, we must modify the tip, where we can do the atomization first. By this modification, we can actually have the interaction between the tip with the sample. So in this case, we didn't perform the modification. We just analyzed the silicon material with the adhesion between the silicon material and the samples.
Yeah, because I'm not sure if we can use atomic force microscopy to see exactly what happened, because you use solid material. Solid material, you may have deformation during the preparation. Okay, it's not really reflecting the exact morphology of your system.
Okay. Yes.
Okay, except when you are dealing with particles and you make a deposit of your particles, you can see exactly the morphology. But in this case, it's a little bit hard. This is why I'm asking this question. Can you go back to slide 43, please?
43, sure.
Yes, please. About nanoprecipitation. And this is will be my last question before the alarm of Montpellier, maybe.
Wait, let me share.
Okay.
Actually, yes, it's from a paper
you
that had been published before. Let me answer.
43, yeah.
Here, this.
Not.
Oh, it's already.
Yeah, it's not this one. Oh yes, yeah, all right. Can you explain how would you perform this, please, again?
The nanoprecipitation via dialysis?
Yes, please. Yes, please.
Yeah, sure. So in this case, pullulan, it's challenging for preparing nanoparticles because pullulan and chemically modified pullulan is only soluble in solvent, which is not possible to perform the solvent evaporation. So it's soluble only in DMSO and the DMF. Therefore, we need to change this strategy for something that we can remove the solvent without further need of evaporation, because if it's the evaporation of the DMSO would take so much energy, and I could, for example, degrade pullulan in this case. So what we do is that we solubilize the polymer and the drug, and in the solubilization in the MSO, we put inside the soluble fraction, we put inside the dialysis bag. We keep the dialysis bag inside the medium, which can be water or a buffer solution, for example. In this case, we evaluated 2 buffer solutions, and we do 3 changes along the day. In this case, we did 24 hours. With the drug, we did 24 hours.
24 hours.
Huh?
24 hours.
24 hours, yes, exactly. We did the 24 hours and the 3 changes along the day.
Okay.
So after these 3 changes, we have the material in a soluble, dispersed solution containing the buffer solution inside. The solvent has already been out. And then what we do is that we can analyze, for example, the particle size using the Malvern with the solution, but we also lyophilize this solution to obtain the particles in a solid way, and then we perform the other analyses such as drug encapsulation efficiency and others.
Okay, yeah, because in dialysis you use active molecule, okay, with the presence of the polymer. How you control that the active molecule is not going to the other part of the solution?
This is a tricky way. Yes, exactly. So
Shall we? That's your tricky way.
No. It's when I say it's tricky, it's because in the methodology it's very difficult to perform. Normally, what we can do is reduce the time. So what we were noticed that when we did the dialysis in 48 hours, there was a massive elimination of the drug. So what we have is reduced the time of the dialysis to see if we could improve the amount of erlotinib encapsulated in this case. So after, this was the strategy that we have made, but it's very difficult. We don't have, normally by this technique, we don't have a higher encapsulation efficiency. We use it when you use the dialysis method, because the erlotinib can leave the dialysis bag since
because since it's equilibrium potential, you may put active molecule in another side.
Exactly, and it can also be observed when we use a lower amount of erlotinib. For example, when we use the polymer drug proportion of 1 to 0.525, since we have the equilibrium, lower concentration of erlotinib in the equilibrium, we had the lower encapsulation efficiency as well. Okay. So we lost many drugs in this case.
Okay, thank you so much. Thank you for this exchange. Thank you, Mr. President.
Thank you very much, Abdelhamid. And you are in time perfectly also.
Thank you so much. I'm afraid about the alarm of Montpellier, that's all.
Okay, so now it's time to your first examiner, Ângela Maria Moraes, to ask you some question. Ângela Maria?
Thank you very much for both the graduate programs for inviting me for being the jury of this very interesting thesis. I thought that the thesis is well organized and well written, and the data that you attained are also well presented and well discussed. It was very nice to read the work. I saw also that you had a very high amount of experiments presented using different techniques. So I am pretty sure that you have used very well the opportunity of the PhD to enhance your formation. So it's very nice. But let me ask you also some questions. I will also point some things that I missed in your work. And I don't know if you have the opportunity to improve the final version of the text, but I will give you some suggestions, because I think that we have to have a very nice written work for the community that was not present at your presentation and that will use your material later. For instance, on chapter 1, I missed a lot the design characteristics that you would expect from the drug delivery system that you would develop in your work in a very objective way. Because you present the objectives and the general and the specific objectives, but I missed like a synthesis of what you were really trying to get, and also to get that again in the conclusion chapter, to see, okay, I checked that, I got that, I did not get that, and then your suggestions would be exactly on how to reach that. Okay. I will not ask you which are the design characteristics, because they were dispersed around the world, so around the text. So I know you know. It's just a comment. Okay. I also missed in chapter 2 a list of the anti-cancer drugs already successfully administered orally, because you showed a very nice set of results for the erlotinib, but you did not show other drugs. Would you have some examples to give now, for instance?
Sorry?
Would you have some examples of drugs that are already used successfully to treat cancer that are administered orally?
Yes, for example, we have drugs in the same classification as erlotinib, for example. If I'm pronouncing right, I think it's vitaminib, but also gentamicin. I'm not sure if I'm pronouncing right because
No problem.
it's difficult to read. But it's other drugs that it's chemotherapeutic drugs and it's already applied in oral administration. However, treating different types of cancer, not necessarily the lung cancer and the pancreatic cancer. But yes, there's other drugs that oral administered already.
I think that if you include this information would be very nice because it enhances the strength of your work. Okay.
Sure. Thank you.
Sure. Another thing that I think that you missed discussing is the fate of pullulan in the body. What would be also the fate of the chemically modified pullulan molecules that you produced? Would they be absorbed? Would they be hydrolyzed? Would they be just eliminated, for instance, in the feces or in urine? What can you tell me about that?
So actually, we were discussing about that at some point. We were discussing about that. I actually performed some testing using for the pullulan degradation, for example. What we expect from the literature, that's for alpha amylase, which is an enzyme that we have in the mouth. It could degrade pullulan, but when we perform it, I'm not sure if the enzyme was active. So we didn't have the result that we are expecting. But as seeing the literature, we have that pullulan, when administered, it can be partially degraded in the alpha amylase. But it's normally absorbed and interacting with the liver. It has a receptor in the liver that can interact with pullulan. In the literature, we can see that. So actually, when we start with this chemical modification, the main focus was parenteral delivery for cancer in liver. So in the liver, since pullulan has this parameter which interacts with which can be absorbed in the liver, but as almost all polysaccharides, it can be metabolized in the body. But besides these two main informations, as how it leaves the body, I'm not sure at this moment. But as understanding that it's a polysaccharide, it may be metabolized and changing the body after the absorption in the liver.
But do you think that, for instance, in the case of going to the liver, it would have to cross the intestine walls to go to the liver?
What it has, if I'm not mistaken, what it has is a receptor in the liver where it gets attached, and it delivers the drug inside the liver by this attachment. But it can, I think since it's a macromolecule, but yes, it can. In my head, let me see. In my head, it normally interacts with the liver, and it can pass through the membrane since it has this receptor.
Yeah, no, but I asked if for instance, to reach the liver, pullulan would have to cross the intestine walls because you are administering it orally.
Yes,
does it cross the intestine walls?
Okay,
Because
yes.
It would probably be mucoadhesive. You showed that. So it would probably not be able, I guess, to cross the intestine.
No, yes, when oral administered, it doesn't go to the liver. It's mainly it stays in the stomach and after it changes. But the liver, when I say it's when parenterally administered.
Okay.
So sorry.
No problem. you prepared your nanoparticles by this dialysis bag method. Do you think that you could use, for instance, supercritical CO2-based technologies to have a better result? Because, in fact, I think that the geometry of your particles is kind of, I don't know, they look like empty bags, all of them. And this is very curious. I would like to know why they have this shape, like a ball that was just emptied. And do you think that another technology would improve this geometry and also the size distribution?
Yes, we tried some technology, some other techniques. We tried the precipitation by dropping it, and we put the solution with a ultrasonic sound with a very strong system. We have a more homogeneous particle size, but the encapsulation was not efficient. So in the nanoprecipitation, we have two challenges. The first one is obtain the particle with the size and dispersity that we wish. And the second one is obtaining the efficiency in the encapsulation of erlotinib. So these two, it's really difficult to combine both of them. So this was the main challenge that we have during the nanoprecipitation. So would be the supercritical CO2 an alternative, yes, but I'm not sure it would make easy to encapsulate erlotinib. But for particle size, yes. Maybe for other drugs, as I suggested in a perspective, maybe for other drugs, it will be valuable.
And also, which other technique would you test, for instance, to obtain the microparticles? Because also the geometry of these particles, they were not quite interesting.
Yes. We basically was obtaining the particles, but the most interesting, do you mean if I can change this technology for obtaining?
Yeah, because you do not have, in most of the cases, in some of the cases you have like spheres when you are preparing the microparticles, but not in all cases.
Yes, it's basically what we can change, as the previous said, what we can change is chemically modified pullulan, obtain a pullulan with a lower molecular weight, so maybe we can have a more homogeneous and a better particle size dispersity. Another alternative, when we change the molecular weight of pullulan, we consequently change the viscosity of the solution. So maybe we can spray dry using high concentrations. But to obtain more like particle size, I think it's not mostly the technique, it's mostly material in this case. The technique also influences.
Yeah, I think that you have, in fact, you already mentioned that you have two problems. You have the material and you have the techniques, because you are having a problem with the standardization of the material. In this, for pharmaceutical technology, is crucial. If you do not have a standardized product, you will be not able to maybe put that successfully in the market. So I would suggest searching for approach that you could improve this standardization. Okay?
Yes.
I was also curious on chapter 3 when you were talking about the chemical modification and copolymerization of pullulan, mostly when you were working with the lysine. I could not understand well how many lysine groups would you put per point, because you would use monomers, but I did not understand well how many, what were the target numbers of groups of lysine.
So this was determined by the degree of substitution. So what we have is that, for example, for each amount, the 25, 40, and 50% was the amount used in mass, in terms of mass, in the beginning of the reaction. However, normally pullulan has a sterile guidance, which makes not possible to totally chemical modify. So most of the monomer were probably not used in the polymerization. We cannot determine the yield in this case. I would like to, but we could not determine the yield, the conversion yield, and the copolymerization. So what we have that we can see is that using the NMR, we could determine how much hydroxyl groups was replaced by the monomer. But how much monomer interacted and grow into a copolymerization, it was hoping to analyze in the GPC. However, the GPC showed a difficult result since it was not possible to solubilize in water, the polymer. So we couldn't solubilize in water. To analyze the GPC, we should have more like a GPC based on the MSO to have a better performance of this analysis.
But can you be sure that you put, in fact, more than one lysine group per point per substitution?
Yes. I believe so, because the carbon NMR show that after the chemical modification, we didn't have the CO2 groups, which is present inside the ring, the NCA ring. So we have this replacement. Therefore, basically, we have the increase in the molecular weight, which is more than the degree of substitution. Okay. And we did not have, after the purification, we did not have the presence of this group, the ring group. So we don't have free monomers in the medium, and the mass that we have was higher than the mass expected.
Okay. And also, let me ask you something about your mathematical modeling of the drug release data. First of all, you used the Kosmeyer-Pepper's mathematical model all over the work, but why did you select this particular model and not others? There are many in the literature.
Yes, and there are many, and in some cases, like, for example, the nanopart, the hot melt extrusion, if I'm not mistaken, it was not well adjusted. However, it was well adjusted for the microparticles, and I wanted to repeat to compare the same kinetic parameter for all the formulations that I prepared. So this is why I applied Kosmeyer-Peppers, and besides with these models, I can also evaluate the solid parameters, that the mechanism that is involved with clearness, with, for example, if it's a diffusion process, more like a swelling, if other mechanism is applied in this case.
Okay, but do you think that in the case of the nanoparticles, you can really draw the conclusions you presented, because your R square is very low, is below 0.82. I don't think that you could do that. Okay. In fact, another thing about this, the use of this mathematical model, is that it's missing a term, because normally the MT is divided by M infinite. So M infinite is a constant, but it varies for each case. And sometimes also, this model can only be used, according to the literature, to the release of up to 0.6 or 60%. So, and you use it for different ranges.
Yes, it was in a way to compare all of them and see if Kosmeyer-Peppers would fit with all of them. But yes, maybe I can change my conclusion in this case, because actually the R square that I have here, it's not efficient. I have other mechanisms, other kinetic parameters that fitted better than Kosmeyer-Peppers in this case. Maybe I should bring for these other parameters as well.
And also another thing that I noticed was that in the same case of the drug release studies, you did not discuss the effect of putting your particles inside the gelatin capsule. And you did not mention the effect on mass transfer that this material would have, because it would also change the kinetic analysis. So maybe you could redo some of the experiments to check using a dialysis bag, not necessarily the gelatin capsule to see what would be going on, or try to model it in a different way.
For the nanoparticle, we did that. We performed it inside a dialysis bag. It was the research that the research student here, undergraduate student here, performed, and we observed that inside when analyzing with using the dialysis bag, we have a more controlled release, and the dialysis bag really influenced it. For ilotinib, it has a strong influence on the dialysis bag in the mechanism of release. But it's further studies that we are performing. For the thesis, we proposed to show the same mechanism of analyzing the drug delivery system. So using the gelatin capsules and the same technique were applied for them.
Okay, and now going back a little to chapter 3, you presented in a figure 38 optical microscopy images of L929 cells incubated in the presence of the biomaterials extracts. But do you think that this particular experiment is conclusive? Do you think that you did not present, for instance, results for control experiments with healthy cells, and the images are quite blurry? So what could you comment on that?
So yes, I think the cells, the image of the cells was more like a complementary analysis to see that the cells were growing inside the polymer surface. In this case, the solution, it was not dyed. However, in the cytotoxicity test, I understand that even though it showed the biocompatibility, it is the cells used in this case was a cell that has a strong resistance. So other cells, more sensitive cells, can be evaluated for having a better comprehension if the polymer effective does not affect the cytotoxicity test.
Okay, I could not see much from your images, I confess.
Okay.
For me, they were not very clear, but I will trust you on that. Okay, I'll thank you again, and thank again the advisors for the invitation, and I give back the word to Professor Jean Coudane. Thank you.
Thank you.
I think that you are mute, Professor. Your microphone is mute.
What a pity. Thank you very much. So now it's time to Sérgio, Paulo, Campana, Filho to ask some questions to Layde.
Thank you very much. First of all, I would like to thank very much to the PhD programs in Brazil and France for advising me to participate of the jury. Thank you to Simone and to Professor Maria Inês for inviting me to do this work. I like it very much. Your work is very complete.
Thank you.
You have a huge amount of experimental data. Are you hearing me?
Yes, yes.
Because my internet signal is not stable, and sometimes the images disappear in my screen. So you are very smart, Layde, doing a double degree program. So you will be recognized as a PhD in Brazil, but also in Europe. It's very nice. I congratulate you and your advisors to making your thesis in this context. I found the title of your thesis very short and very informative. I comment on it because usually my students, my PhD students, like very much to elaborate very long titles. And you succeeded to inform most important things you did in your thesis with a very short title. I liked it very, very much. Your abstract is okay. It's okay. It's very brief, short, and informative. And we can have, in reading it, a very clear vision of your work. But I think it missed some quantitative data. So maybe you reserve it to the manuscript you will submit to journals. But even in your thesis, it would be interesting to have some values. Let's see, the values of the zeta potential, the average size of the microparticles, and so on. And also, as somebody mentioned too, it misses a comparison of your results with the other DDL systems. I mean, those based on pullulan, and also those not based on pullulan, other biopolymers and synthetic polymers, and also other anti-cancer drugs. It would be very interesting. I don't know, Ângela Maria asked you, and I haven't heard the answer. The final thesis, is that we are considering, or you have time and room to modify it as the final version?
No, I'm still doing the modifications for submitting the final version. Yes, the corrected version.
Okay, because
so I can follow all the
suggestion that I will not mention here, but I will send to you in your email address the file with my suggestion and some questions I will not put in now. Okay?
Thank you.
But the manuscript is very well written. There are some errors, there are mistakes, but if you have room to correct it, I would recommend you to do so. Okay?
Sure.
The organization of the thesis also is very good. The reading is fluent. I liked very much to read your document, so it's very well. But I have another question about the choice of pullulan. I will insist in it because I understand that the group in Lorena is working with the production of pullulan by fermentation a couple of years. That's it, I think. So yes. It's a natural way to work with this biopolymer. Very interesting. You listed a lot of advantages of using pullulan, but there are other polysaccharides that also have the same advantages, the same characteristics. And my question is why you didn't use pullulan as a primary standard to calibrate your chromatographic system?
It's because at the moment that we did the characterization, we didn't have the standard in the university because it was very expensive and we couldn't afford. So after we had a professor here who could afford the standard, and I think it's 1 or 2 years ago, we already have the standard here. So maybe I can perform the preparation of the polymers again and analyzing the GPC comparing to pullulan as a standard, because now we have here in the university, but before we didn't, so it was a challenge for us.
But you know, when using PEO as standards to calibrate your columns, you have added an error.
Yes.
Intrinsic error because the chromatographic system of SEC responds to hydrodynamic volume. And as PEO and pullulan have different stiffness,
yes,
for the same molecular weight, you have different hydrodynamic volumes. So it's very important to have a second analysis if you can, using more trustable results, I would say. About the delivery of ERL, I would like to hear from you if it is released mainly in the stomach or in the duodenum.
Okay, so the release, the solubilization mainly occurred in the, can you hear me?
Yes, yes.
So the solubilization mainly occurred in the stomach medium, since erlotinib, it's a pH, pH has the sensibility to pH, so it's soluble in lower pH, so it's going to be soluble in the stomach. However, the limitant in erlotinib is that when we change, when the drug comes from the stomach to the duodenum, the pH change. So what we have in the body is that we have the recrystallization process. It reduces the soluble fraction of erlotinib and consequently impacts in the bioavailability of the drug. So in this thesis, we mainly evaluated if we could improve the soluble fraction after the pH change, and it was possible to see, especially for the amorphous solid dispersion containing Klucel, that we saw an improvement in the soluble fraction. However, what we can propose is a oral administration with a long time retention inside the stomach for erlotinib to evaluate if erlotinib can be absorbed as well in the stomach. And the change in the pH won't be necessary.
Okay.
You can just...
But think about the absorption in the stomach. Why 2 hours? You are supposed that the oral administration is made and the individual has the stomach empty with any food. That's it?
Yes. Yes. Normally, yes. We have that erlotinib can have some interactions with the food. So what we propose as we evaluate only the pH influence. We didn't compare to, for example, stomach empty or
it would be very, very difficult.
Yes, the ideal is the empty one. Yes.
But yet on the gastric juice, you use the hydrochloric acid aqueous solution of pH 1.2. It mimics the gastric juice pH. But in the gastric juice, you have 2 proteins, mainly enzymes as pepsin.
Yes.
It would have some effect on the release of the drug if you use the gastric juice with pepsin. Because
yes. What we have in the research group is another test that was performed for previous study of Professor of another PhD student. She evaluated the 2 different mediums for the dissolution test, and it was evaluated a more simulated gastric simulation, and she had a dissolution profile when for the soluble fraction of erlotinib when this medium was a more complex medium containing the specific characteristics that simulates the oral administration. In my case, I wasn't going to, it was an option to work with the same medium as she worked before, and she has already published this medium that she worked before. I had the option to do so, but I would choose to work with the simple medium, which just simulate the impact in the pH to see the influence of the polymer in this case.
I wonder if the material, the copolymer of pullulan and polylysine, it would be susceptible to hydrolysis by pepsin in stomach juice. Maybe it would impose a new mechanism of release, the drug release.
It's interesting. Yes, we can discuss for further evaluation of the impact of pepsin in the drug release in this case. Yes. Thank you, Professor.
About the sec of your pullulan derivatives, I think the comparison of the average molecular weight, average molecular weight, is not the better comparison you can do. Because as you modify the chemical structure of pullulan, it modifies its hierarchical behavior inside the columns. So you could, as important in the three derivatives with polylysine, with degree of substitution of 13%, is the S is 0.13,
yes,
0.22, and 0.25, I think.
Exactly.
You could normalize the difference of molecular weight, average molecular weight, by expressing it on terms of average degree of polymerization. So you take into account the degree of substitution of each sample of the grafted polymer of pullulan. Maybe the comparison would make more sense than just comparing molecular weight, because they are different. You could evaluate the occurrence of depolymerization from one to another derivatization by normalizing the values of molecular terms of average degree of polymerization. It's just a suggestion. You can reflect it and decide to do or not, okay?
Thank you.
The DRX spectra you shown in your thesis show to us that there is a great difference between the profile of the drug, the anti-cancer drug, ERL. It's very crystalline. We can see the signals, very sharp, very strong. But your polymers, with your eDAUT encapsulation of anti-cancer drug, they are semi-crystalline. They are not as crystalline as the anti-cancer drug, but they have semi-crystalline, some order. And it's possible to treat your diffractograms in order to calculate, to estimate of crystallinity of your pullulan derivatives. You just said, okay, they are amorphous. They are not completely amorphous. They are not as crystalline as the anti-cancer drug, but they have some crystallinity. And I don't know if you take some effect on the release of the drug, but you can work a little bit more with this experimental data.
Okay.
I agree with my colleagues. Indeed, Ângela Maria said that the AFM results are not conclusive. I don't know if they add very much important data for your thesis. Okay?
Yes.
I have a question. When you work with spray drying, there are several parameters that you have to control or to vary to analyze which one is more important.
Yeah.
Haven't you think about using chemometrics to plan the set of experiments you carry out to analyze these systems?
Yes, it was a possibility, and it's a good strategy as well to perform the planning experiment. But at this case, with the material, we couldn't do that because we didn't have a higher amount of the polymers to perform this characterization. Because when we work with chemical modification of pullulan, we work with, for example, we started with 5 grams and the final material is 2 grams and 50. So we already lost 50% of the material. And due to that, we couldn't take so much material to France, and it was not possible to perform an experiment, design experiment, because we should focus at this moment in the main parameters and choose the best conditions based on these main parameters for reducing the amount of experiments that we were performing, and then we could prepare the formulations based on pullulan and pullulan DAE. So it was more like how to use less material, and this is why we didn't perform it, but it's possible. It's a possibility for sure.
About the thermal analysis, when you show us the TG curves and you discuss some data, I missed a table expressing the T onset, T maximum, and the corresponding mass loss. It would be very helpful to understand your discussion, looking at not only to the TG curves, but also to a table with the quantitative values of temperatures and the mass loss. It would be very, very helpful.
Okay.
I recommend you to do that or to think about that. Okay. About the same images, you have not used any software to treat the images and try to estimate the dimensions, the average dimensions. Why?
Because we performed after the diameter determination of particle size by another technique, but it's a possibility. I can try to perform this. Now at the moment when I did, I didn't know the software is possible to perform it, but now I know. I have working here in the laboratory, and I heard about this software where I can determine the particle size from the same images. So it's a possibility for me. I'm thinking about calculating the particle size from the same images, yes.
Oh, my internet fell. Okay. Are you reading?
Yes.
Yes. The last question about the cationic amphiphilic pullulan derivatives. You did 2 consecutive derivatizations on pullulan main chain to insert cationic groups, okay, and then to insert hydrophobic groups to have an amphiphilic derivative of pullulan. Why don't you call the final material prepared from this polymer, this derivative, why didn't you call it micelles?
Because I have the graphene copolymer, so the structure that I have from the nanoparticle is probably not a micelle, since I don't have like a block copolymer. And probably what I saw in the literature is that basically the nanoparticle structure, the self-aggregation structure that I have when I have this type of graphene copolymerization is more like a polymeric aggregation than the formation of micelles. So this is why I didn't use the micelles term, because I'm not working with block copolymer, and basically what I saw is that micelle is more related to block copolymers.
So you cannot affirm that the anti-cancer drug is inside the nanoparticles or microparticles.
Yes. It may be inside, or it may be in the surface. Exactly. I would like to perform a thin image, or be more conclusive or to understand more the particle size.
Okay, I found your thesis is very, very nice. Your presentation also was very, very good. And thank you very much. I finish.
Thank you very much, Professor Campana Filho. And now I give the floor to Ana Paula Lemes. I don't know exactly the pronunciation, I'm sorry. Who is your last, just before me, examiner.
Thank you. First, I would like to thank Layde, Simone, Marina Israel, and the postgraduate program for the invitation. It's a pleasure to stay here participating of this defense and contribute to discussion. In my opinion, the theme proposed in this thesis is amazing, is fascinating. It was a complex study with many stages of work. You, Layde, investigated many methodologies, trying to the oral administration, target the oral administration of the drug with pullulan, and you did an excellent job. The text is well written, presenting many interesting results. It's clear that you made it with determination, dedication, and passion. I'm sure that you have learned a lot through this process. Congratulations to you and your advisors. Well,
thank you.
Of course, I have some questions about your work, corrections, suggestions. I highlighted some parts of your text and made notes for you to discuss with your advisors if these points are relevant or not. And I will send you the file after the defense is concluded, okay?
Okay.
Well, I will ask you only the most important questions, in my opinion. My task is easier now because the most part of questions were made. So I will focus directly on the part that I think, I believe I can contribute more. That is the chapter 5 concerning hot melt extrusion, okay?
Yeah.
Well, in general, in this chapter, sometimes I'm curious or confused a little about the chosen concentrations, for example, of drugs that you select for masses, select masses for solubility tests, for example. Why this concentration? Why this blend composition? I think that you should explain the choices a little more, or just remind the reader, because we have here a lot of information to process. So it's hard to remember all stages, all choices that you did in your work. So don't worry to repeat the explanation about your choices, okay? The first point that I would like to ask you is on page 161. It's about extrudability of polymers. In section 5221, in my opinion, it seems that you describe the results without explain the methodology used in this test. Could you clarify how the test was performed? For example, what were the temperature, screen speed, time, the extrusion parameters that you try with the pullulan?
Yes, sure. So with pullulan, from the literature and our experience in the laboratory showed us that it's not possible to extrude. Even if we put high temperature, for example, close to 200, what we have is a possible more close to 200, 210. We can have the degradation and melting. And sorry, and what we have as well is like the pullulan gets stuck in the screw when we try to extrude. This was not observed on here, but this was observed also here in the Brazil with a single extruder. We have a extruder here with a single screw. And when we put on the pullulan, even though we increase temperature or we increase the screw, we get pullulan stuck inside there, and it gets like a foam. I don't know why, but it's not possible to extrude. It's expand and it's stopped all the extrusion process. So probably due to the transition temperature, pullulan, it's not possible to observe melting temperature in pullulan. It degrades before, and the TG, when it's completely dry, the TG gets close to the degradation temperature. So therefore, pullulan was not possible to extrude alone, that's not at all. And it was necessary to blend it with other polymer, and then I did all the calculation to select which one would be a better option in this case.
Okay, I believe you. I think the result is very similar when we try to the extrusion of starch polysaccharide, so it's the same. But here I think it's better as it is a methodology section. You put all things that you explained to me, and after in results, if you have, of course, maybe a picture about how the material you obtain after to try extrusion the material, okay? Because here it seems a result and not a methodology. No? I know that you try change the temperature and time and this kind of things, but I agree with you, it's impossible because it's a polysaccharide and it's not work, of course. Did you consider the possibility of using a plasticizer instead of a blend?
Yes, I consider, and I even started the test. I mixed pullulan with other different plasticizers to see. I even started a virological test, but what we observed is that plasticize, for example, glycerin, if I'm not mistaken, I forgot.
Yes, glycerol.
Exactly. Glycerol, exactly. Glycerol, it was the one that I could reduce the TG of pullulan, but as an interesting alternative, we chosen to blend with a polymer that is possible to extrude and it's already applied in the pharmaceutical field. With the plastificant, we have some limited amounts that can be applied. So it was better to, instead of use a plastificant, I can use a material that I know the amounts that I can apply.
Okay. For me, yet in this chapter, the most important point is on the page 162. Because in the text, I saw the equation 9, but it's not correct in the thesis, no? But you correct it in your presentation.
Yes.
Yeah, I saw.
Yes, it's
Yes, because in presentation the equation is correct, so you have to correct in the thesis.
The thesis.
Okay, it was an important part, and the equation 10, I'm not sure if it's the same of the presentation and the thesis. Okay, because I tried to find the same values with the equation that was in the thesis, and it's different from the table 14. Okay, but I saw that you correct in your presentation. Okay.
Okay.
Don't forget to do that in the text. Well, about the table 14 in page 168, I'm not sure what value you used for the fractions. For example, here in table 14.
If I use the filaments or the microparticles?
No, delta T, for example, table 14, okay? Hensel solubility parameters. Yes? Here, for example, for the calculation of fractions that you used in the diagram, what delta T you used? For example, pullulan, 42 or 47?
No, 42. I
42.
use it. Yes.
Okay.
I use it in the diagram. What I did is that I calculated the force, which depends on each contribution of Hansen solubility parameter. And then I calculated the force and I plotted all the force corresponds to the Hansen solubility parameter. So, which corresponds to the first delta T. It's not the literature. The literature was just a comparing the results from theory to what I calculated.
Okay, but these forces, delta D, delta P, delta AD, it's from the cited literature or not?
Yeah, I calculated with the contribution of each organic function that I have.
Okay. Okay.
Yes,
okay.
I found it in the literature, which I mentioned in some way, but it's mentioned that where I found the literature. But it's a book, a handbook that I have all the parameters exposed there.
Okay. Now I understood better that what you did. And in my opinion, in this part, I think after the diagram, you can explain a little more about the importance of similarity between the values, solubility parameters. For example, in the book of Polymer Science by Canivarolo, there is it is mentioned that empirically the difference should be lower than 1.7. So to deeper your discussion, I think that you can explain a little more about the importance. It makes the solubility process be spontaneous. Okay, so just a little more about here. And general way, you mentioned in page 169 that the effect of on drug solubility depends on the cell concentration. And after, on page 172, in page 170, you mentioned again the improvement of soluble fraction of drug with cell. So, yes. Why do you think it's happened? Why? An explanation, a hypothesis about this, what's happened, some chemical interaction?
What we see from the literature, normally it's involved in the presence of polymers in the mixture, in the soluble fraction with drugs. We can have, I think I even explained a little bit in the end, is that we can have this not exactly interaction, but a more stable system where, for example, the elucidity recrystalline form with the presence of the polymer dispersed in the middle, it will take a longer time to start the process of recrystallization. So the polymers makes the solution more stable and delay the process of recrystallization, inhibiting it. I believe in case of Clucel, it's not exactly, it can be a chemical interaction, it can have a chemical interaction in this case. Since we have, for example, Clucel is also a polysaccharide, you have hydroxyl groups, and it can have, for example, hydrogen bond or something like this. But in the literature, it's not possible to find specifically the types of interactions that can have, just that some polymers can improve the solubility, the fraction soluble of these polymers. What I did is that when choosing Clucel, I chose Clucel with lower molecular weight, and what I saw before is that the molecular weight can also have this influence in the stable solution containing the drug.
Okay. And about the degradation of filaments concerning extrusion on page 172, you wrote that as the extrusion temperature increased, the filaments turned more yellow, indicating degradation of polysaccharide. I agree with you, but was there any quantitative analysis to verify this degradation, or was it based only on color?
No. I was thinking about performing, for example, solubilizing the polymers and see HNMR, the HNMR, for example, to see if I have like sugar, oxided sugar, for example, to see if the yellow comes from the sugar. What I believe is that the yellow comes from pullulan, the presence of pullulan. Since with Clucel only extruded, we didn't have this physical change, this color change, and what I think we can perform in this case is a chemical characterization to see the chemical modification after the thermal procedure in the extrusion process, to see if the yellow corresponds to the degradation effect of the polymer, starting the degradation of some chains of pullulan.
But have you considered performing a TGA, for example, a thermogravimetric analysis?
Yes, it's an
Or
alternative.
colorimetric analysis to verify this.
It's easier.
It's easier, yes. I think that it's maybe you have a good result to publish and to prove that the yellow color that you said, it's an indication of degradation. Okay, so
okay,
a suggestion. And about the particle size, you said it is observed that particles containing higher amounts of ERL presented a larger particle size. Well, what could be the explanation for this? Sometimes I think that it's missing a little more explanation or hypothesis or suggestions of what happened in your system after you show the results. I think sometimes it's missing.
Yes, I thought about many suggestions for this case. So first, thinking about the technique, it can be like, for example, in the manipulation of the samples in the cryomillet, for example, when I put the samples inside the cryomillet, I put different size of the filament. So it can be from the preparation of the microparticles, or it can be also from change in the resistance of the polymer. For example, mechanical resistance of the polymer. Exactly.
Yes, yes.
With the chemical modification.
Yes,
because it was significant different from the others for the copolymers.
Yes. It's a crystal, for example, of the drug. You can, you will change the mechanical properties of the polymer, of the blend. So I think that you can try to explain it about changing the mechanical properties. Maybe the material is change your hardness or softness. Okay, try to explain that. I think that you could have a good explanation here about that. It's an interesting effect of the drug. My alarm, the drug in the mechanical properties of the material. Okay, so that's my last question. I use my 20 minutes.
Okay.
And I would like to finish. Thank you again, you all, for the opportunity.
Thank you.
Thank you very much, Ana Paula. You were in time. So, now, before giving the floor to your two supervisors, it's my turn to ask you a few questions. So, before asking you some questions, I would like to thank Maria, Inês, and you, Layde, for your invitation as a member of this thesis jury. Regarding the work carried out, first of all, I would like to say that I particularly liked the manuscript of this thesis. It's very well written and perfectly clear. The ins and outs of the thesis are well and clearly presented in the introduction. The objectives are well specified, and the choice of the various products is justified, except perhaps for pullulan, which I'll get to very soon. And I particularly appreciated the various didactic graphics. So for all this work, congratulations.
Thank you.
That said, I still have a number of questions. Don't be afraid, I'll be brief, less than 20 minutes. First of all, I would like also to thank Professor Fardim, who asked many of my questions, especially concerning synthetic polymers and why pullulan. And concerning pullulan, that definitely raises questions. I have some precisions. The first one is why pullulan, for example, rather than dextran. Their structure are more or less the same. There are only hydroxy group, okay? And the advantage, the physicochemical advantage of dextran is first, its glass transition temperature is under 0 degree. And maybe that the glass transition temperature of pullulan is high, maybe too high for the extrusion and so on and so on. Okay, and you mentioned it page 54, yes. So it's the first point. Second point, you mentioned that there is in page 48 that chitosan is the polysaccharides most used in the production of EL, nanoparticles. So, why pullulan versus chitosan? Why? And it's true for pullulan. Then I have other questions. Why pullulan
Pullulan.
instead of
No,
quitosane?
of course, when it comes to polysaccharide, working with pullulan for a long time. So since before I started my PhD, I have been working with pullulan, and what I see is that polysaccharides is a huge spectrum of possibilities. So we have polysaccharides which can be obtained by natural form, from natural sources, or we can have polysaccharides obtained by fungus fermentation. So I think pullulan has a huge advantage compared to chitosan, is that it's more homogeneous, the chain. For example, chitosan, we can have different degree of substitution as well. And since it's obtained from natural source, it can vary the properties. When you have, for example, what they have someone giving the pullulan in a different person working with another pullulan, you can change the properties from the polysaccharides. This is experience that we have here in the laboratory, is that different chitosan can have, you may optimize the polysaccharides to have similar properties in both cases. But chitosan is already cationic, so it has some advantage in pullulan because I didn't need to chemically modify to have the cationic property. But I see dextran, every time that I look for a paper to work with chemical modification of pullulan, dextran is always my reference. So I always ask myself, why not working with dextran? So I think dextran is an alternative for sure for chemical modification, and for the application, the drug delivery is important because it has a lower TG than pullulan. But pullulan, it's novel, it's not a lot explored, and it can be further explored, and we can find different applications. It's a promising material that we may further study. So this is my...
Okay, thank you. So I'm not specialist in pullulan, dextran, or chitosan, but I was wondering if the advantage of chitosan was the amino group. Maybe, or not. So I have a second general question. Where is this question? So, it's concerning the choice of microparticles for anti-cancer treatments. Anti-cancer drugs are generally highly toxic, even for healthy cells. And this is why often researchers try to have a vectorization, a targeting of the drug towards the cancer cells. Or this is possible with, for example, nanoparticles, but it is not possible with microparticles. So I understand that the administration, the oral administration, is a good parameter. Okay, but microparticles, why microparticles?
So at this case, erlotinib is already a drug applied in the oral administration. So the microparticles in this way comes mostly for the improvement in the soluble fraction of erlotinib, not specifically to develop a targeting agent in this case. As I previously said, in the beginning of the thesis, the main purpose was to develop a polymer which would be targeting when parenteral administered. However, for pullulan, for erlotinib, it was not possible to develop a parenteral form of erlotinib using the nanoparticles, for example. So we mainly focus in keeping the oral administration. However, produce different formulations, different encapsulation systems for trying to improve the solubility of the drug that has been already applied in the market. So it was mostly due to that, but microparticles came as an alternative, and when we proposed the microparticles, we aimed to obtain the amorphous solid dispersion, which is an efficient way to improve the solubility. However, we saw that the solubility between both polymer and drug were not the best conditions for obtaining the amorphous. So we had the crystalline. And this is why I think, I don't know if I answer your questions, but the microparticle is an alternative for improving, for example, surface area, wettability of the drug, and improving, therefore, the bioavailability of it inside it during the oral administration. This was, we hope it, and to conclude that it's necessary further in vivo study, for example.
Okay, so I was wondering, because you mentioned nanoparticles in your last chapter. Yes, so I was wondering why all the first chapters you mentioned only microparticles. Now I understand why. So I have to go for many questions, very interesting work. Okay, when you prepare your copolymer with blocked polylysine, okay, you compare the structure of the copolymer with the structure of the pullulan alone, with the monomer blocked lysine alone, okay. But in my opinion, spectrum of homopolymer polyblocked lysine is missed. Because, always in my opinion, when you prepare your copolymer, you obtain your copolymer, but also an homopolymer polyblocked lysine. Yes. How can you make the difference between the copolymer and the homopolymer? When you try to evaluate the substitution degree, for example, it's not easy. It's not easy because if you have homopolymer, and I believe that you have some homopolymer, you cannot measure the degree of substitution of the blocked polylysine on the pullulan.
Yes, this is a question that I have asked myself, for example, especially for the nanoparticles. So what is the influence of the homopolymers present in this mixture between copolymerized pullulan and homopolymers based on PZLL? What is the influence in this nanoprecipitation? So what I have is that it may influence in the aggregation, in the increasing the particle size, for example, but it doesn't. What I think is that it doesn't influence in the encapsulation process because polylysine, it's hydrophobic, so it's mostly going to precipitate and may be like insoluble and not dispersed in a dispersion solution. So what in fact can encapsulate erlotinib is the copolymer, and what we have is like the influence, especially in the particle size, when we have this homopolymer. This is what I have, and as an alternative to improve and try to remove this homopolymer, I thought about like a selective precipitation, dialysis using another solvent. I thought about many strategies.
In my opinion, it's not easy.
Yes. But even though it's not easy,
it's
the experience we have here.
Yes, but you mentioned the problem of solubility. Of course, the homopolymer is probably not soluble in water, but the copolymer is water soluble.
The copolymer?
The copolymer? No, not no. So it's very, in my opinion, there is some homopolymer. Okay, but it's very difficult to separate homopolymer and copolymer.
Yes, and another thing that we have is that pullulan that we started has like a molecular weight with different size. So another question that I make myself is how can I ensure that it's homogeneous, the replacement along pullulan backbone is homogeneous. So this was another question that I made to myself. I tried to think about techniques to evaluate it, but it's really hard when it comes to graphic polymerization.
Okay. Yes, and another indication is in page 107, not important, when you show GPC, size exclusion chromatography, chromatograms. Your chromatograms are multimodal. There are many peaks on your sec chromatograms. It's not very good. It's not very good. And this is also why I presume that there is copolymers, pullulan alone, copolymer pullulan avec EDC and so on, and blocked polylysine, and homo-polylysine, homo-blocked polylysine. So this is probably one of the reasons that your chromatograms are very difficult to interpret.
Yes.
Because when you have a polymer, a copolymer, okay, maybe you can have a large distribution, but you cannot have a multi-peak. So there is a problem. I've not the solution, but there is, in my opinion, there is a problem in this side. And it's time for me. Allez, 2 minutes. Talk. Yes. You mentioned sometimes, I don't know exactly who, there is a mistake concerning PEG. I don't know exactly where, but you say that PEG is a biodegradable polymer. Polyethylene glycol is not biodegradable. It can be eliminated from the organism by renal filtration, depending on its molar mass, but it is not biodegradable.
Okay.
You inject polyethylene glycol, it remains polyethylene glycol. So it's not very important here, but be careful with this. Alors, last question, very important because I didn't understand. It's concerning for the in the last chapters, maybe that concerning the solubility of erlotinib, of the copolymer, and so on. Maybe that when you try to incorporate drug in your copolymer, I believe that you have always a precipitation of free drug in your mixture. Some drug is incorporated in your microparticles, and some drug is not incorporated in your microparticles. So it's also, in my opinion, very difficult to measure the incorporation ratio of drug in your copolymer.
Yes.
But the problem, in my opinion, is that your copolymer is not water soluble. The drug is not water soluble. So when you work in an aqueous medium, you will always have problems of precipitation, polymer precipitate, copolymer precipitate, etc. Part of polymer, part of drug are precipitating. So another problem you have to think. And of course, as usual, I have no indication to give you. There is a general problem of this. And the last question, where is my last question? Okay. You observe, it's page 208, concerning the drug release. You observe a delay. You mentioned a delay, however small, should have an impact on the therapeutic window for oral administration of the molecules. The delay is 5 minutes. If I okay. Frankly speaking, 5 minutes is really enough.
Yes.
What was your aim? 1 minute, 5 minutes, 10 minutes, 1 hour, 1 day, 1 year? What is your aim?
Mm-hmm.
Because in my opinion, 5 minutes, it's not enough. It's not enough.
Yeah.
What's your opinion?
Okay.
I don't know really how to proceed, but
I think to evaluate the impact of the 5 minutes. It was necessary. It is necessary to test like in vivo test or blood solution. Yes.
Maybe it's enough. I'm
Maybe.
not convinced. Yeah.
Exactly.
Right. So, Bo, I'm sorry, but it's time. Yes, it's time. It's time. So, I would like to congratulate you once again for your work, both for the clarity and precision of your manuscript and also for the didactic aspect of your presentation. And finally, I'd like to give the floor to your two thesis co-directors, supervisors. The first one is Maria Inês Rey.
Yes. Thank you very much. I'd like to start by thanking all members of the jury for accepting to evaluate this work for this rich, interesting scientific discussion you could have now with Layde. So thank you for your suggestions and all critical points mentioned that you will take in account in the final correction. So, but I'd like to say some words more. So first, I'd like to thank Simone, my colleague, who invited me to co-supervise this PhD thesis. It's important here to explain that you have complementary research activities, Simone and I, and this have enabled us to carry out research work, ranging from the synthesis to the application of the polymers in the health field, as was done in this thesis. So the thesis is a very ambitious project, and the first question I made it to Simone and Layde was, why pullulan? Why to modify pullulan? What can you do with these modified polymers? Because I was not convinced of the interest to modify and to test pullulan for these different systems. So the idea of modify pullulan for an intentional application, so to test new systems, drug delivery systems, by using some processing techniques you have been studying or working with. It was interesting for us. But in this thesis, you could see, I think the most important is the different skills, scientific skills Layde could develop, because you have different critical points. The first was the solubility of the polymer. So when you use these hydrophilic polymers, pullulan, and for which process, and how adapted the new modified polymers for the process of our interest, spray dry and hot melt extrusion, in particular for us. And erlotinib is a molecule you have been working a lot, and the challenge is to produce oral formulations for oral chemotherapy. It's a very challenging molecule because it has a very, very low solubility in basic medium. So the idea was to improve the control of the amount of erlotinib released in the gastrointestinal tract. The results obtained in this thesis show, in fact, that these polymers are not the best systems for erlotinib, because they cannot avoid enough the recrystallization. But we are not developing a commercial product in this thesis, so I think it is very interesting to all the work done to adapt these polymers to the process, or the process to these polymers, in fact. So the questions linked to the choice of another polymer for a blend composition to allow hot melt extrusion of the modified polymer. The solubility of the erlotinib in these polymers is also very low. The modification of spray drying to produce a solution instead of a dispersion when using pullulan. So they are different interesting scientific points treated in this thesis, and I think it was very interesting for Layde. Layde is a very serious, curious, and proactive person, and these are all the qualities of a good researcher. So I think she learned a lot with this thesis. And she was, I thank her for the motivation to develop this research thesis, because some critical points are really critical, and to start with the very low amount of material to work with, the polymers produced in Brazil, and you did not have a lot of polymer to work a lot here. But I think, as you could say in this discussion, the work has a good scientific level, and was interesting to produce a new doctor, in my opinion. So thank you all for participating in this doctor production today. So that's all for me. I will give the floor to the president.
Thank you very much, Maria Inês. And the last one from Brazil, Simone Medeiros Sampaio. Maybe that my pronunciation is not at the top. Sorry.
I'd like to thank again all the jury members for careful evaluating the work, the Layde's work, for your suggestions and your comments. all suggestions were pertinent, and the next days we will work on the modification of the manuscript based on the member suggestion. Just a few words. I started. There is long time that I work with polymers for encapsulating drugs. I started in my PhD, in master study. I started working with synthetic polymers, and after a certain time, I changed the polymers for biological polymers, and for this reason, pullulans appeared interesting for these applications. And Layde was my first. I don't know if everybody knows, but Layde was my first graduate student. She started with the master student, and after she concluded the master and started the PhD. It was a pleasure working with her. I think we could in this last years we could learn a lot together, and we could also obtain good results. Obviously, the work needs some others characterizations to publish new articles, new papers, and we also in the next months, I hope we can also prepare these new papers. I think it's important, and but in general, the work gave us good results, and I think now Layde is a prepared professional to act in any areas. And I hope a success life for her. Thank you, everybody.
Thank you very much. So now it's time to end. Thank you all for your participation. So now the jury will now retire. That is to say, to connect to the second link communicated by Maria Inês.
Okay.
So
Okay, I'm leaving this month.
we are leaving for a few minutes.
Leave us on to the second one so you can discuss it. Excuse me.
Okay. Yeah. Okay.
We have to go to another link.
I think so that we have to go to another link. They are moving.
Okay.
Hamid, j'ai envoyé les mails. C'est bon?
Everybody is here in Ça y est, Layde.
Hello?
Layde is here.
Yeah.
Layde, what a moment. So Layde, the jury has met. If the word met can be used at all, since we are all on video conference, and they have judged your defense and awarded you the degree of Doctor of the University of Toulouse. He also congratulates you on the quality of your work and your excellent presentation. So, once again, congratulations, Dr. Layde Teixeira de Carvalho. So now, after that, it's time for the host. You have to read. If not, we cannot sing.
Yes,
we have to hear.
I have here?
In English.
English, okay. Just opening here. Okay, so in the presence of my peers, with the completion of my doctorate in process and environmental engineering, in my quest for knowledge, I have carried out demanding research, demonstrated intellectual rigor, ethical reflection, and respect for the principles of the research integrity. As I pursue my professional career, whatever my chosen field, I pledge to the greatest of my ability to continue to maintain integrity and in relationship to knowledge in my methods and my results.
So now we can consider that you are Dr. Layde Teixeira de Carvalho, and we can applaud.
Congratulations.
Congratulations.
Yes.
Congratulations.
Thank you.
Congratulations.
With all my
Thank you.
congratulations for your defense. It was a remarkable defense. Sincerely.
Thank you. And thank you all.
Congratulations.
Thank you, Professor Hamid. Thank you all for accepting the jury of this thesis defense. I think we have made the best choice in the evaluators. You all gave me contributions to correcting the thesis to my future as a researcher in polymers, hopefully. And I would like to thank you all for being here. And thank you, my advisors, Professor Simone, who started with this thesis idea, come from her. And she always accepted me since the master's degree we started together. And as her first PhD student, I'm glad to have her as an advisor. I think we all grow up together, and with Professor Inês, I would like so much to thank her for kindly receiving me in France. She gave me all support that I need in France. It was amazing working with her. She gave me all the support for her experience to improve my test, to improve the writing process. And I think if this is like it is now, it's also because they were helping me during the process. And I would like, if you don't mind, I would like to thank all my friends that are here watching and on YouTube, everyone from Rhapsody and from here at University of São Paulo. I would like to thank everyone that helped me and my family also, who gave me all the support, and my boyfriend that is also here and was a kind helpful for me in the end of this moment. So thank you all for being here and for helping me.
Nice to meet you. Have a nice week.
Yes. And I wish you all the best for your future career, of course.
Thank you.
All the best.
Thank you.
Bye-bye.
Bye-bye.
Bye. Thank you.
Bye
Thank you
bye.
all.
Bye-bye, France, and
Congratulations,
bye-bye,
ladies.
Brazil.